So we've calculated the electrical conductivity of metal. Why don't we try calculating the thermal conductivity of a metal using Boltzmann transport theory? We can write that the heat flux is actually written in a very similar way to the charge flux. The only difference is that we're not just counting the number density, we're counting the amount of energy carried as well. So I'll include a prefactor, which is E minus mu, which is the only difference really in the calculation, which is essentially the energy measured relative to what the energy would be at 0 Kelvin. So we're really looking for differences in energy and that are driven by a temperature gradient. Then we'll do our usual thing where we replace the non-equilibrium distribution function with the portion from Boltzmann transport theory, which involved the gradient of the equilibrium distribution. So in this case, the gradient is caused by the temperature gradient. So I'll write that gradient term as df dt times dt dz. So the temperature will be a temperature gradient in the z direction. So obviously the temperature gradient in the z direction doesn't appear in any of the stuff being integrated over, so I can pull it outside the integral and then identify that everything that's inside the integral is actually the thermal conductivity due to the movement of electrons. So let's expand that the thermal conductivity out. So the electronic thermal conductivity, I'll do the usual thing where I'm going to convert it to spherical coordinates instead of Cartesian coordinates. And when I go to do that, I'm going to skip a couple of steps that I had shown for the charge transport case. So I'm just going to immediately write that as an integral over energy instead of over k, and then the direction cosines will be done separately in a phi integral, and of course the integral over theta is just from over all 2 pi. And I've already showed that the integral over the cosine phi sine phi integral turns out to be 2/3, and of course the theta integral is 2 pi. Then we can combine all that stuff together. It basically turns out to be like 1/3. And then all the stuff in the integral, so the E minus mu times df dt times the density of states integrated over energy. Also with a Vg squared tau integrated over energy. And if I look inside the integral, I'll notice something really cool, which is that the front 3 terms are actually exactly the same terms that appeared in our heat capacity integrand way back in the statistical thermodynamics section. And so for a similar reason, so all 3 of those terms, or at least the leading 2 terms, change quite rapidly inside the integral, whereas the last few terms don't change rapidly inside the integral. And so what I can do is identify that integral without actually going through and doing the entire integral is actually 1/3 times cv squared times t, evaluated at the Fermi level. And so that's our solution. It's 1/3 cv squared times tau is the electronic thermal conductivity. And if you're studious, you'll notice that that's also a fancy way of saying 1/3 CVL, which is the exact same formula that we had gotten for a gas, like a gas of actual molecules earlier in the class, which is why this is sometimes called an electron gas.